Today, we're going to talk about something that might just flip your understanding of the sun on its head. It's a theory that challenges the story we've all been told about how stars are born. So, yeah, let's dive right in. You know the story they teach you in school, right? Giant cloud of gas, gravity does its thing, it gets super hot, and boom, fusion starts. A star is born. But what if that's just part of the story? What if the most critical moment, the real beginning, has been hiding in plain sight this whole time? Because think about it. When we look at the sun, it isn't just a chaotic mess of hot gas. It's got structure, it's got patterns and cycles that repeat with mind-boggling precision. A simple collapse doesn't really explain where all that deep underlying order comes from. And that right there, that's the real puzzle we're going to try to piece together today. All right, so let's dig into this sun-sized puzzle. Because the story we've been using, as good as it is, leaves some seriously big questions on the table. Okay, so this is the classic model, the story we all know and love. Gravity's the hero pulling gas and dust together. The pressure and temperature in the core just skyrocket until eventually hydrogen atoms start smashing together to make helium, releasing just an insane amount of energy. That's the moment we call the birth of a star. But here's the thing, and it's a huge thing. That model is fantastic for explaining where the sun's energy comes from, but its behavior? Not so much. It doesn't tell us why we see these beautifully organized things like sunspots or coronal holes, or why the sun has that famous 11-year cycle, plus a bunch of others. How does all that complex order just appear out of chaos? And this is where things get really interesting. A new idea, called the HSF theory, comes along and says, hey, maybe we've got the birthday wrong. It suggests the sun's real birth happened way earlier, before a single atom of hydrogen ever fused. So get this. The HSF theory says the sun's birth wasn't a thermonuclear event. It was a geometric one. The most important moment wasn't about fusion igniting. It was about the formation of the very first stable, continuous surface. This surface, which the theory calls S, is the real game changer. So you can see the difference laid out pretty clearly here. The standard model is all about the thermonuclear ignition, but the HSF theory says, nope, the real magic happens when that geometric surface forms. And here's the kicker. It claims that surface is precisely where all that mysterious order comes from. Okay, so a surface. How on earth can a simple surface impose all this incredibly complex order on a giant ball of gas? Well, it turns out it all comes down to a very specific sequence of events. Let's walk through this timeline because it's pretty cool. You start with a cold cloud, kind of lazily spinning. As it contracts under gravity, like a figure skater pulling their arms in, that spin gets faster and faster. And then, bam, phase 2. That's the big one. The first stable surface forms, and it instantly switches on an organizing field. This means, by the time the fusion engine even turns on in phase 4, the fundamental blueprint for the sun is already there. It's already set. So there you have it, the 1, 2, 3, 4 of it all. The formation of that surface is like flipping a switch. It takes this messy, disorganized cloud, gives it a boundary, and in doing so, it activates this powerful organizing force right on the sun's skin. So what is this organizing field? Well, it has a name, Lk5. And the easiest way to think about it is like the surface of a bubble. Before you have a bubble, there's just air. But the second that film forms, you get surface tension, which allows for all sorts of waves and patterns. Lk5 is kind of like the surface tension for the new baby sun, setting up all its fundamental patterns and rhythms from the get-go. But, a system like this with all this new energy could easily spin out of control. You need something to keep it stable. Enter player number 2, Lk4 macro. Think of this as a giant stability battery. It's hooked up to the surface, and its whole job is to soak up excess energy from that organizing field and then release it nice and slow. It's the regulator that prevents runaway chaos and locks the sun into those stable, long-term cycles we see today. Okay, so this all sounds like a really neat, elegant story. But in science, a good story isn't enough. A really good theory has to make predictions. It has to be testable. And this is where this whole idea moves from being interesting to being potentially revolutionary. All right, first big prediction. The HSF theory says that all those big features we see on the sun's surface, they're not random, not at all. They should appear in very specific places. So remember our bubble field? Lk5, well, the math behind it predicts it should create these specific bands of activity across the sun, almost like lines of latitude on Earth. And here's the wild part. When astronomers actually look at the sun, the places where we see these long-lasting dark coronal holes and these super active hot belts, they line up beautifully with those predicted bands. That's a huge piece of evidence. Next up, let's talk about the sun's heartbeat. Or rather, its heartbeats, plural. We all know about the 11-year cycle, but it turns out the sun has a whole family of related rhythms, and the standard model has a tough time explaining why. HSF says, I got this. It's kind of like building a piece of music. First, you have the Lk5 field. It sets the fundamental notes. Think of these as the basic rungs on a ladder. Then you add the sun's own rotation, which takes each of those notes and splits it into a little chord, a whole family of related periods. And finally, our stability battery, Lk4 macro, provides that slow, overarching baseline, the long-term solar cycle we all know. It's a system that naturally creates this rich, complex family of rhythms. Now, this all sounds pretty convincing, right? But here's the most important part of any scientific theory. Can you prove it wrong? It has to make specific, concrete predictions that astronomers can actually go out and check. That's how we know it's real science. And this theory does not shy away from that. It basically hands astronomers a checklist. It says, go look for this. Map the coronal holes. They better line up with our predicted bands. Track solar flares. Their timing has to match our predicted rhythms. You can even measure the sun's exact shape and look for a tiny rinning on its edge at specific frequencies. Each one of these is a pass-fail test. If they fail, the theory's in big trouble. That's really putting your money where your mouth is. So let's just be super clear about the stakes here. This is not just a minor tweak to the old textbooks. If this stuff holds up, it means the fundamental organizing principle for a star isn't the nuclear fire in its core, it's the geometry of its surface. That is a massive shift in how we think about stars. And that leaves us with this incredible final thought. We have spent centuries defining stars by their internal fire. But what if a star's real story, its actual identity, is written right there on its skin? If we've been looking in the wrong place to understand our own sun, what else out there in the huge, wide cosmos are we completely misunderstanding?